Okay, welcome to Intro to Automation, where we're going to talk about Six Sigma. In preparation for that, I want to give you a little bit of a background on how manufacturing works. So we're going to be talking about a very, very typical machining operation, which is cutting off a length of steel. And to do that, let's take you through a little bit of a presentation. So let's share my screen and let's talk about Six Sigma and manufacturing. So we're going to talk about a typical manufacturing operation. We're going to talk about how we measure the results of that operation in a typical manufacturing environment. And then we're going to talk about charting the results, because Six Sigma is often depicted as a chart, and we're going to talk about how that chart gets created. And then finally, we're going to talk about Sigma itself. This is a very typical manufacturing operation. That guy is a typical manufacturing guy. In this operation, you have a piece of stock that gets clamped in. As you can see, there's like a clamp down here. Here, let me turn on my highlighter, laser pointer. All right, see this clamp down here? That clamps this round stock in place, and then this giant saw, there's like a blade right here. You can't quite see this blade, but there's a blade that goes around a big oval. And when you drop down this whole saw assembly, it chops off whatever steel materials inside the clamp. You obviously need some coolant, you need some oil to do this consistently and do it well. The coolant flows around the blade and keeps the blade lubricated and cool. The way you keep the length consistent is you put a stop on the other side of this length of stock, and you push the stock up against the stop. You chop the stock in half or whatever length you need, and then you lift the saw back up, and then you pull out your finished cut piece, set it in a tray, and then start over again. Loosen your clamp and so forth. So this is a very typical manufacturing operation. The only thing you really care about in this operation is the length of the stock you're chopping off. So in this operation, all we care about is one measurement, the length of the stock. So typically we would measure the length with a caliper. If it's a small part, it might be a tape measure. If it's a large part, or you might, if you need a very accurate measurement, you might use some of the larger calipers or other measurement systems like a laser system. But typically there's a measurement step that occurs right after you chop the part off. So my problem was, when I was first doing this when I was 16 years old, I did not measure the parts. No one told me to measure the parts. I didn't know anything. I was a 16-year-old kid who just got thrown onto a machine, and I should have been measuring the parts on a regular basis. I should have been pulling out a part, measuring it, putting it back in to this tray, and then making sure that I was being very consistent in my cutoff. The second thing that I didn't get told was that the part absolutely couldn't be too short. It could be a hair long, but it absolutely could not be too short, because they're machining material off these parts, and by machining material off, they couldn't unmachine if it was cut off too short, but they could machine it back down if it's cut off too long. So measuring the results is very, very important. Generally, in a manufacturing operation, they're going to measure samples every 3 or 5 or 20 pieces, depending on the volume of pieces running through your shop. They're going to measure samples. When you first start machining parts, you probably need to measure every sample. Then they document those samples, and they document on what's called a typical X bar R chart. So that every sample, see the samples are on the bottom here on the chart. So every 10 minutes they pull a sample, they measure it, and they see how far it is from its target measurement. So typically you'll see the target at a line in the middle, and you have an upper limit and a lower limit. And if your part stays in that limit, you're good. Everything's good, right? So this part can be up to an 1/8 of an inch long, but it can only be a 1/16 of an inch short. You don't want it too short, it's a problem. So those might be your upper limits. and the center, the actual target length, is right in the middle. And so by measuring the samples, you see where that sample fell. Is it too short? It's down here at the bottom. Is it too long? It's up here at the top. So you just keep measuring your samples. And typically you would document your measurement on a chart like this so that you can visually see how you're doing. If you start to see that part trend down, you get shorter and shorter and shorter, you may stop what you're doing, check everything in the manufacturing process, because you don't want that to trend down below your lower limit. And now you have to start throwing away parts. So you're measuring up these parts and wow, that part's getting shorter and shorter. Stop, let's figure this out, and then restart the process. So this is what typically, they call this an X bar R chart. I'm not going to get into why they call it that way, but it's basically just documenting the measurement. So over time, say over a day, you might collect all those measurements, all those samples, and on the bottom of the chart, you would have the actual measurement. And then on the y-axis, on the side of the chart, you would have the number of times you found samples that were that far off. So say 50 was your target, right? So your mean, your center of your counts are at 50. But then you find that there were some you measured up at 49, some were at 48, some were at 47, 46, but they tailed off. None of them were so short that they were below 46. Good, especially if your limit was 45. And none of them were larger than 55. Great, so your limit at the high end, nothing went higher than the highest limit. So by counting up the numbers of samples in each of these categories, you're able to create this chart and then apply a graph to that chart, which sort of smooths it out. That smoothing chart gives you this, what's called a curve, a histogram with a normal curve. A normal curve just takes the actual counts, the frequency of the measurements, and applies a smoothing curve to it. So standard deviation, and I'm not going to get into the formula for it because it's not important, is used, it's calculated based on the number of deviations based on the mean, where the center point is, the process average, and the total number of deviations you have. And so typically one standard deviation is just down the slope of your standard curve, right? And 2 deviations is twice that, 3 deviations is 3 times that, 4 deviations is usually the outside of the curve, and if you go to 6 deviations or 6 sigma, these are way out there in terms of the limits, usually, of your measuring process. So 6 sigma means that you've kept your process really tight, and if nothing achieves 6 sigma, then you've kept your process nice and tight in the center of your target length, in this case, for our cutoff process. And I've given you the definition of standard deviation, and don't worry about lot and trading, but it's a standard deviation, a statistical measure that represents the rate of divergence from the mean in a data set. Okay, it's the rate of divergence from the mean, from the average, approximately. We're going to use mean and average as the same thing, even though in statistics they aren't quite the same thing. We're not going to get into that. It's the rate of deviation from the mean. You know, how much variation there is. So when we talk about keeping a process within 6 sigma, that means that my sigma has to be so small, right, that there is a virtually impossible chance that my process will deviate out to Six Sigma. It's a virtually impossible chance. I'm keeping everything so tight and so precise that my upper and lower limits, that normal range, is so far away from all my actual measurements that it's like a 99 point, and you'll know the number shortly if you watch the video. It's a high number odds that you'll have that process ever go beyond the mean. And if it starts to, you've got to make a change to your process to fix it.